In the previous video, we introduced the III-V PV technologies and discussed the structural properties of the III-V absorber materials. In this video, we will look at the electrical and optical properties of the III-V materials. To that end, you will learn about the electronic band dispersion diagram of gallium arsenide. We will also look at the absorption characteristics of gallium arsenide and compare it with that of crystalline silicon to understand the differences between both materials. Let's first begin with a small recap of the band dispersion diagram that was introduced earlier in this course. In a crystalline lattice, the atoms are arranged in a certain pattern that repeats itself. However, the pattern is not the same in every direction. Depending on how you cut through the lattice, you could, for example, end up with the 100 surface, where each silicon atom has two back bonds and two valence electrons pointing to the front. Another possibility is the 111 surface. Here, every silicon atom has three back bonds and one valence electron pointing towards the plane normal. The exact energy level of the conduction and valence band depends on these directions. In other words, the exact energy level of the conduction and valence band depends on the position of an electron in the crystalline lattice. This figure shows the different positions or directions that an electron can occupy in a crystal lattice. This also means that the momentum of the charge carriers can differ with the various directions in the lattice. Here the L direction represents the 111 surface and the X direction represents the 100 surface. As we know, an electron can move through a crystalline lattice if it has enough momentum. We can therefore build a graph with the energy level on the vertical axis and the momentum of the charge carriers on the horizontal axis. The charge carrier momentum is also known as the crystal momentum. By solving the Bloch function for a certain position in the lattice, you can obtain the energy levels of the conduction and valence band edges. By connecting these energy levels with the specific crystal momentum of the various crystal orientations, you obtain the electronic band dispersion diagram of a material. The white area represents the energy levels in the forbidden gap. The band gap of a material is defined as the difference between the lowest energy point of the conduction band and the highest point of the valence band. For silicon, these 2 points are not vertically aligned. This band gap is an indirect band gap because the charge carriers must change in both energy and momentum to be excited from the valence to the conduction band. The dispersion diagram of gallium arsenide is quite different from that of crystalline silicon. Gallium arsenide has three well-defined valleys at the X, gamma and L position of the crystal lattice. The smallest band gap occurs at the gamma valley, where the valence band aligns vertically with the lowest energy level of the conduction band. Gallium arsenide is therefore a direct bandgap material. For a direct bandgap material, only transfer of energy is required to excite an electron from the valence band to the conduction band, but no transfer of momentum is required. At its lowest point, the bandgap of gallium arsenide is equal to 1.42 electron volts. The fact that gallium arsenide has a direct bandgap energy strongly affects its absorption characteristics. Plotted here is the absorption coefficient of crystalline silicon as a function of the photon wavelength. This red line on the horizontal axis indicates the wavelength corresponding to the bandgap energy of crystalline silicon. With a bandgap of 1.12 electron volt, the corresponding wavelength is about 1100 nanometers. Gallium arsenide has a high bandgap energy of 1.42 electron volt, corresponding to a wavelength of about 870 nanometers. The visible part of the spectrum, where the solar irradiance is the most powerful, is indicated by the colored region. As we can see, the absorption coefficient of gallium arsenide in the visible spectrum is significantly higher than that of silicon. The same is true for indium phosphide, which has a direct bandgap corresponding to a wavelength of 925 nanometers. This means that for a similar absorber layer thickness, the III-V materials will absorb a much larger fraction of the incident light. This is because for an indirect bandgap material, it is less likely that energy from a photon with an energy exceeding the bandgap can excite an electron, since it also requires a change in momentum. As you may recall, silicon also has a direct bandgap of 3.4 electron volts, which corresponds to 364 nanometers. For energies above this direct band gap, silicon absorbs just as much as the III-V materials. So in a direct bandgap material, an electron only requires a change in energy to be excited. But the reverse is also true. An excited electron in a direct bandgap material does not require a change in momentum to recombine. The dominant recombination mechanism is therefore radiative recombination. The fact that radiative recombination is dominant in high-quality III-V materials, a process in which a photon is emitted upon electron-hole recombination, is why they are widely used in electronic light-emitting devices such as lasers and LEDs. But how about the other types of recombination? Shockley-Reed-Hall recombination is caused by defects and is present in any material. In a good quality III-V single junction solar cell, Shockley-Reed-Hall recombination is negligible. However, as you will learn in the next videos, Shockley-Reed-Hall recombination might become significant in certain type of multi-junction devices. Finally, there is Auger recombination. As Auger recombination is a free particle process, the Auger recombination rate strongly depends on the charge carrier densities for the electrons N and holes P. Under normal circumstances, Auger recombination is insignificant for direct bandgap materials. However, for an N-type semiconductor under high injection conditions, when a very large amount of charge carriers are generated, Auger recombination might also become important for direct bandgap materials such as gallium arsenide. Such high injection levels occur, for example, for concentrated photovoltaics. Now time for a recap. In this video we learned about the electrical properties of III-V materials. We first looked into the electronic band dispersion diagram and learned that these materials are direct bandgap materials. Further, we also learned that this direct bandgap gives rise to radiative recombination losses and a high absorption coefficient, which are characteristics that have to be kept in mind while designing these solar cells. With this, we complete the study on the properties of III-V materials. In the next video, we will look into the application of III-V materials in multi-junction solar cells.